So I think it's about time to talk about networking. We've got 34 people watching, which is probably a record for me. The video will be going up on YouTube pretty much as soon as I can get it online after this stream. But the idea is that we're going to talk about networking. So, like, not from networking for dummies sort of a perspective. You know, it's not going to be suitable for young children, not because they'll be cursing, although they might be. So you're kind of expected to have a certain amount of competence with computers and that sort of thing. But I'll try my best to answer questions as we go along, and I'll try and get my laptop in a slightly better position so I can see the chat a bit better, so I can do as good a job as I can of that. So if you have questions about whatever it is I'm whittering on about, pop it in the chat and I'll do my best. Networking then. Networking is when two computers talk to each other, right? So, or two or more, but the simplest case that we can start off with is two. And I'm going to pretend that they are connected to each other with a network cable. So both machines have a network interface. But they're just bits of wire, right? So there has to be some kind of convention that they use in order to talk to each other. Just like random voltages on a wire isn't really going to mean anything to a computer. So each computer has a network interface, which would be like a network card or something like that. Although, you know, if you're in the cloud, you might be a virtual interface. If it's a laptop, it might be Wi-Fi. For us, we're going to stick to physical network cards for now. So each network card has this thing called a media access control address, or a MAC address. Some people call it a hardware address. I'm going to call it a MAC address. And they kind of look like this. So here's an example of one: 50.465D 549423. And this is something that was set at the factory where the card was manufactured. And it's often possible to change it on many network cards. But in theory, at least, it's globally unique. So every network card that you buy will have a different one of these. It doesn't necessarily have to be globally unique. The important thing is that every network card on your network has a unique address, and we'll see why shortly. So data is sent around the network in little chunks called frames. So when you've got two computers talking to each other, you imagine they want to talk back and forth, and when you add extra computers, they want to talk too. So you don't want one computer to be talking all the time, so no one else can. And for a variety of other reasons, we want to chunk up data into these little frames. And basically every frame, and you can think of it as being a little bit like an envelope, I suppose, for like the physical mail system, has a source and a destination MAC address. Just like when you send, you know, a real letter in the mail, it has a destination address, otherwise it can't get to where it's going. And if you want people to be able to reply, you need a source address too. So you might be wondering, you know, if I want to send a message to someone, how do I know the address, right? I've got two computers connected together with a piece of wire. How do I know what the destination MAC address on my frame, on my little chunk of data is going to be? And the answer is, well, you don't, or at least not initially. But you do know the IP address because you, as a user, in some way, shape or form, you tell your computer what the address you want to talk to is. So it might be one like this, 192.168.0.1. This is an IPv version 4 address. We're not going to talk about IPv6 today, partly because I don't want to be here all night, and partly because I don't think you really need to know in order for sort of understanding networking basics. So there's this real neat trick, right, where a machine, if it knows an IP address, can ask the whole network if any other machines have that IP address. And because machines ignore frames that don't have their MAC as the destination, you can safely send frames to as many machines as you like. But there is this special anyone or broadcast MAC address of FFFFFFFFFFF, or you could pronounce it FFF, I suppose. But this is kind of a special destination address, and it means everybody should pay attention to this. Doesn't matter what your MAC address is at all. If you see this address as the destination, you should pay attention to it. So a brief aside. Again, it's been a while since I've looked at this slide deck. So if you want some information about your network interface on Linux, you can use ifconfig, interface configuration tool, or you can use the IP tool, which is technically newer and not deprecated, but at the same time, I know which one of these is much easier to remember, so we'll mostly skip over that. Cool. So, what happens when one machine wants to talk to another? So we're going to have two theoretical machines here, machine A and machine B. So I've given machine A an IP of 192.168.0.1 and a MAC of all A's, or make it nice and easy to remember which one is A. Machine B has an IP of 192.168.0.2 and a MAC of BBBBBB, or I guess, just to really hit home that this is machine B. So the very first thing that machine A is going to do is send a frame with this information in it. So it has the source MAC address, that hardware address is all A's because that's the machine it's coming from, and the destination MAC is all F's because it doesn't know where this machine is it's trying to talk to, so it's going to do a broadcast. It's going to talk to everybody, and it's going to have some data in that frame as well, which is not written in English text like this. It's a slightly different format, but for our purposes, this is good enough. It's something like, who has 192.168.0.2? Tell 192.168.0.1, which is machine A. So every machine on this network, although in our case it's only two machines because they're both connected with a bit of wire, is going to receive this frame saying, who has this IP address? Tell this IP address. Machine B is going to see that frame with all F's as its destination and go, oh, this is broadcast, I need to pay attention to this, and read the data and go, oh, that IP, I'm not going to say the 192.168, that 0.2, I have that IP, so I'm going to respond. So it sends out a frame onto the network with the source MAC of its own, or B's, and the destination MAC of all A's, because it knows where the request came from. It was in the source MAC of the original frame. And the data is going to look something like 0.2 is at BBBBBBB. So now both machines store those IPs and the corresponding MAC addresses in a thing called their ARP cache. So this process of finding out the MAC address for a machine given its IP is called the Address Resolution Protocol, or ARP. And once you've done it once, you store it in a cache so that the next time you need to send a message, you know where it's going. So I quite helpfully decided to illustrate this. You'll have to excuse my drawing. So each box here is a frame. Machine A sends out a frame from A to all F's, asking who has 0.2, tell 0.1. Machine B sees that message, that frame with all F's as the destination, the broadcast, goes, oh, I've got that IP address, so I'm going to respond. So a frame goes out saying, from B to A, 0.2 is at all B's. It's at that MAC address. Machine A will receive that. Now it has its information. And now they can talk to each other. So, the very next message that happens, machine A wants to talk to B again. But this time, machine A has that MAC address in its ARP cache. So it can easily send a frame with the source MAC of all A's, a destination of all B's, because it knows where it's going. And inside that frame, as we've been calling it, this little chunk of data, is an IP packet. So networking conjures up many visions of layers or things being encapsulated in other things. We have a frame which contains the Ethernet stuff, and in that is a packet which contains IP stuff or Internet Protocol stuff. So we get the MAC addresses in the frame contains the packet, and the packet is the IP stuff. And it's really similar, so we have the source MAC and the destination MAC. In the packet we have the source IP and the destination IP, and then we have the data. And when we saw data in the last slide, that was actually an ARP packet. And you might wonder, why have a MAC and an IP? What's the point in these two different things? And one is you need one to look up the other, but also machines can have lots of IP addresses, like per MAC address as well, if you wanted to. And there's other reasons as well, which we might touch on later. Just checking the questions. ARP. Someone said, can you turn that broadcast off, or is it fundamental? You technically probably could, but it would probably require some driver hacking and things like that, and then you also wouldn't be able to do any networking, so you probably would not want to do that. So here's how sort of the full picture looks. When you have the MAC address you need in an ARP cache, you get the frame with the from and the to, or the source and the destination MAC addresses, and then inside that you have the packet with the from and the to IP addresses, which is an IP packet, and then some data, but we don't really know what that is or care about it right now. So, like, a useful thing you can do on your own machine is you can see your neighbors, the other machines on your network. So IPN on a Linux machine will show you your ARP cache. And there's a way to do it on Windows as well, but I forget what that is because it's been a long time. And IPN might work on a Mac as well. Maybe someone in the chat knows. So this is a list of some IPs on my network, or on my old network at least. And then this is the name of my network interface, ENP3S0. And then this is the associated MAC addresses for all of those different IPs. So given this ARP cache, if I want to send a packet to .1.23, the MAC address is sat there waiting, ready to go, so the network drivers can stuff that into the destination MAC field. Nibium asks, please tell me this stream will be saved. Yes, it'll be on YouTube, so don't worry if you don't manage to catch something. Cool. So, like, what if you have more than two machines, which is pretty common on a network? I know that there's, I think it's probably 30 or 40 machines on my network. Not all PCs, laptops, tablets, phones, internet-connected toasters, that sort of thing. But pretty common to want more than two machines to connect to each other. And pretty much the most simple thing you can do to connect more than one machine, in modern-ish times anyway, is to use a thing called a hub. So hub's pretty dumb, not very smart. It does pretty much exactly one thing, which is if it receives a frame on one physical port, it sends that same frame out to all of the other ports as well. And then it's up to the computers on the other end of those ports to decide whether they are going to pay attention to a frame or whether they're going to ignore it. And they work kind of okay-ish, but they're very, very slow. So, like a 10 megabit hub is pretty, or was pretty common back when I first started playing with networks. You might get 100 megabit if you're lucky, but usually only if you've only got sort of two machines on them. And you get these things called collisions, which is machines all trying to talk to each other at the same time. And we can do better than that anyway, but what a hub looks like is machine A is trying to send a message to machine B again. They're all connected to a hub. And machine B does receive that frame, but machine C and D also receive it because that's what the hub does. You can kind of think of it as a repeater. So the way we can do better then is with like network switches, which is something that probably most of you will be at least a little bit familiar with. And the difference between hubs and switches is that switches are a little bit smarter, a bit more efficient. So they do this clever thing, which is they remember the source MAC addresses in the frames that they've seen on each port. And if you see a frame with a source MAC on a particular port, you know that that machine is physically connected to that port. Might be via another switch, but somewhere down that piece of wire exists a machine with the MAC address that was in the source on that frame. So in general, ideally, frames only get sent to the port a MAC address is actually connected to once the switch has learnt what machines are on each end. But that tends to happen pretty quickly. As soon as you sort of turn the switch on, it will act like a hub, but then within probably seconds, if not fractions of a second, basically every machine connected to it will have sent at least one frame, and the switch will have figured out where everybody is. So in the event that a switch doesn't know where a MAC address is, it acts like a hub, sends it to all ports. And an interesting thing is it can never really learn where FFFF, all Fs, that broadcast MAC is. So if it ever receives a packet like that, it always acts like a hub and everything goes out to all ports. So big advantage, we get fewer collisions, it's much faster. You can get gigabit switches are common. 10 gigabit is also increasingly common in data center networks, but also in some people's home networks. Or if you're a fan of Linus Tech Tips, for example, you might know that they do run like 100 gigabit switch networking over fiber and all sorts of crazy stuff for their big servers with lots of storage, and so all our editors can use stuff. Very cool to see people using that stuff. So for a switch, looks kind of like a hub, but this time, C and D, they don't see a frame, provided the switch has already learned where machine A and machine B are and what ports they're physically connected to on the switch. Switches. So, machines can talk in this way only if they're kind of directly connected to each other through hubs and switches, or just a network cable between two machines. And if they want to talk to a machine that's off the network, they need to do something else. So we need a way to kind of define what a network is. If I'm a machine trying to talk to some IP address, I need to know whether I can talk directly to it by setting its MAC address as the destination in the frame, or whether I need to do something else that we'll talk about in a bit. And the way that we do that is, as well as each machine having an IP address we can configure it with, we give them a thing called a subnet mask. And you've probably seen these if you've ever delved into the network settings on your PC. So this one, 255.255.255.0, and that's used in combination with the source and destination IPs to decide if they're on the same network, or in this case the same subnet, because our overall network is going to be made of many subnets. And I always thought that these are actually really difficult to understand, 255, 255.255.0. What does that mean? And unlike just about everything else in the world, I think it's actually a lot easier to understand in binary. So 255 turns out to be an 8-bit binary number, which is all ones. So the rule is, if two machines are on the same subnet, if the bits in their IPs match, where the corresponding bit in the subnet mask is a 1. So let's take a couple of examples to kind of see what that really means. So these are two machines that are on the same subnet. So we've got 192.168.0.1 and 0.2, and they both have the same subnet mask, 255.255.255.0. And in binary, what that looks like is, all ones for the 255s, and then all zeros for the 0, because it's 0. And then these are these two IP addresses translated into binary here. And like I said, the rule is, if the bits are 1 in the subnet mask, then the ones in the IP have to match the corresponding ones. So if you imagine this as a series of columns here, everywhere there's a 1, if these match, then they're on the same subnet. That's the rule. So we can see here, these bits differ. This is 0, 1, and this is 1, 0, which is in decimal 1 and 2. because you got the 1's column, the 2's column, the 4's column, the 8's, and so on. But because there's zeros here, that's fine, they can differ. But if we look at two machines that are on different subnets instead, so this is on 0.1 and 3.1.2, we can say there's a 255 here in this corresponding segment. And if you know about subnetting already, you will know that means they're on different networks. But why they're on different subnets really is because here, where there are 1's in the subnet mask, the corresponding bits in the two addresses differ. So when any machine is going to send out and going to try and communicate with another machine using IP, the Internet Protocol, pretty much the first thing it does is it looks at its own IP address, the destination IP address, and its subnet mask to figure out whether it can talk to that machine directly. And if it can, it will either look in its ARP cache to find the MAC address, or it will use ARP to figure it out, like we talked about at the beginning. And if it turns out it's on a different network, it's a little bit scuppered, for now at least. We'll figure out what it does soon. So kind of a quick aside, because who wants to say 255.255.255.0? It's a really large amount of syllables. I really don't want to do it. There's also this CEDAR or CIDR notation, the classless interdomain routing notation. And all this is how many consecutive 1's there are in the subnet mask. So this sort of classic 255.255.255.0 you might hear referred to as a /24. And what that means is there are 8, 16, 24 1's in a row in the subnet mask. And they have to be contiguous as well. It's worth pointing out. It's not valid to have a 0 in the middle of here and then go back to 1's. They all have to be stacked towards the left-hand side. So other network sizes you might hear about a /8, for example, which would be just 8 1's, and then these would be all 0's. And that makes the network bigger. So here we've got up to 255, kind of, 254 machines that we can have all on one network. If these were 0's as well, then we would increase that by a factor of 255 for a /16, and then another factor of 255 for a /8. So this effectively controls the size of your network. So we mentioned we use subnet masks to figure out, can one machine talk to another one directly? And if it can, it just does. And if it doesn't, it does something else. And this is what that something else is routing. So if I want to send a packet, an IP packet to a machine on another subnet, on a different subnet, I don't set the destination MAC address to be the machine that I'm talking to, because I can't figure out what it is. It's on a different subnet. I instead use my default gateway or some router on my network. So a router usually has more than one network interface, like physically, more than one MAC address too. It effectively sits on two different networks at once. And it always has more than one IP address, at least one per subnet. So in an example here, we've got machine A, which is on subnet 1, as a MAC of all A's, an IP of 0.1, 192.168.0.1. And then our second machine has a MAC of all B's, but it's on a different subnet. So we can see there's a 255 here in the subnet mask, and it's on 1.1 instead. Different network. We can't talk directly to it. The router, though, or router, I'm going to say router, has two MAC addresses, two IP addresses. It sits on both networks. So it has MAC 1, which is all C's, and sits on our first network, and is at 0.254. And its second MAC address is all D's, and it sits on the other network at 1.254 instead. So an example hop between networks might look something like this. So machine A wants to hook up to B. They're on different subnets. So machine A sends a frame using the MAC for its default gateway, or the router on the network, as the destination MAC. So the source MAC is all A's, that's machine A, and the destination MAC is all C's, that's the first MAC address of the router. The source IP is 0.1. The destination IP, though, is machine B's IP. So you can think of it as the IP information stays the same across all of the networks, but the MAC addresses, the hardware bits, kind of get a little bit messed with. So the router receives the frame, and it sends on the second network a frame with a source MAC as its own, its second MAC address, and the destination MAC becomes all B's. Because the router is on both networks, it can talk directly to either machine. So the source IP remains the same, the destination IP remains the same. So what the router really did between taking a message from one subnet and passing it to another is it modified the source and destination MAC addresses. Machine B receives the frame from the router. So in my own unique style, machine A sends a frame, source, all A's, that's its own. The destination, though, is C's, that's this interface on the router, but the packet has source IP of machine A and the destination IP of machine B. And then on the other side, when the routers handle it, the source becomes this interface on the router, and the destination MAC address becomes machine B's MAC address. And again, the packet, the IP bit, that stays the same. And that means, when machine B wants to reply to machine A, it knows it should reply to using a destination MAC of all D's, because that's where it came from. So the router, because it handed the message over in the first place, pretty much knows, it almost guaranteed to know where to send the message. So there might actually be a situation here where you have multiple choice. So machine A sent the frame to what we call its default gateway, which is something you'll probably see if you configure the network interface manually on Windows, for example. There's a field to put it in, default gateway. And that's usually something like 192.168.0.1 or .254 on many home networks by default. But it doesn't have to be that way. You could have more than one. So you can have a thing called a routing table, where you have different options to choose from. So we've got 3 routers sitting on this network, theoretical network here. We've got 0.254, .253, and .252. And they each represent a different network. So if my machine wants to send a packet to anything starting 192.168.2 something, it will use this gateway. If it's .1 something, it'll use this gateway. And then all zeros here, this is the default gateway, which is .254. So we're not going to touch too much more onto routing tables or anything, but I just want you to know that they exist, and it's not the case that there's always one router. And on sort of internet infrastructure and that kind of thing, almost always there's going to be more than one. So multiple networks get connected together with routers, and we call that the internet, effectively. There's a bit more to it than that, and how these routing tables get set up is a subject that we're not going to be covering, but I can still give you a reasonable idea of how it all fits together, to be able to understand how things are going on. And so I'll just have a quick check in the chat. Assassin Routing 9 says, any good sources to learn networking? Well, I don't know how to take that. This one, I hope. Again, I tend to just Google things. Wikipedia is remarkably good. A long time ago, I read a big, thick orange book called Networking Complete, which talked about token ring networks and that sort of thing. And I'm not entirely sure whether I'd recommend it, but that's the one that I read. Okay. Cool. Let's find out what's next in the slide deck. Oh yeah, so there's this thing called the OSI model, which you might have heard of, the 7-layer networking model. We're mostly going to ignore it, because largely because when it gets to layers 5 and 6, it's a little bit annoying, and well, mostly 5, but also because people smarter than me came up with an alternative that they call the Internet Protocol Suite. It's a much simpler model. And as with all models, it's not always a completely accurate description of everything that exists. It's just a way that we came up with to be able to talk to each other about things, in this case networking, and being reasonably on the same page. So these 4 layers then, at the bottom we have what they call the link layer, and the unit of data in the link layer is frames, which is the first thing we started talking about, so MAC addresses, that sort of thing. Then we have the internet layer, layer 2, and the unit is packets, which is where we do IP and IP addressing and routing and that sort of thing. So we've talked about that too already. But then we get another couple of layers we haven't really touched on yet. So the transport layer, which deals with segments. We get things like TCP and UDP, which we'll talk about. And then on top of that, we get the application layer, where the unit is just data. All of the segments from the layer bow get assembled. So you, at least in theory, don't have to worry about that stuff anymore. And we get things like HTTP, which you're hopefully familiar with, FTP, SMTP, many other different application layer protocols. And the rule is, as you go up the layers, you are increasing the amount of abstraction. So, down here in the link layer, you have to care quite a lot about the physical network and how it's connected and that sort of thing. On the IP layer, you have to care about routers and stuff. On the transport layer, you have to care about things we're going to talk about in a bit. But by the time you get to the application layer, you can kind of almost pretend that there's just machines that can talk to each other in some continuous fashion, and you don't care about packets and segments and things anymore. So that's why we have this kind of layered model in which to talk about things. Alia 2 asks, do I have to know the OSI model, or should I just know the Internet Protocol Suite? I think it's kind of useful to be aware of both, because these models, like I say, are a way to help understand what's going on, but they're also a way to help people communicate with each other. So I can have a conversation with someone in which I say, oh, there's this application layer protocol, and they know what I mean without having to explain it. So, the OSI model very quickly, is very similar. So we have like the physical layer at the bottom, which we kind of ignored on the other one, and its unit is bits. And you can think of it as, there's voltages on a wire with some additional error correction and things like that. Ben Eater has a fantastic series on networking on YouTube if you want to know about how they physically work, like hooking wires up to an oscilloscope and stuff. Then we've got the frames, which kind of matches directly. The packets on the network layer, that kind of matches directly, as does the transport layer. But then we kind of miss out this session and presentation layer. So the session layer often doesn't really map to things that well that people tend to know about. You can argue the presentation layer is where you do things like encryption and TLS. And then we have the application layer, which maps kind of directly. In the Internet Protocol Suite, we tend to just kind of group things like encryption into the transport layer. TLS stands for Transport Layer Security. So you would certainly hope it ends up in there. So it's kind of like grouped in with things like TCP and UDP, which we'll talk about. So let's talk about TCP. So, so far we've mostly thought about one-way communication only. But it turns out the network is unreliable. People with JCBs dig up cables in streets when they shouldn't, and and break people's connections. And also, routers sometimes drop packets. You hear about packet loss. And I always used to wonder, where do they go? They can't just sort of fall off the side of the wire somewhere, escape through the insulation at the side. And the answer is, these routers have, if we're talking in a simplified way, a couple of chunks of memory in them for a receive buffer and a send buffer. Because one machine sending voltages on a wire, And if the router's not ready to read those voltages at this exact moment in time, it's not going to see them. They're going to be gone. So you have a bit of code effectively being hardware in reality, but reading those voltages off the wire and throwing them very quickly into a piece of memory where something written in higher level code is going to process them and do all kinds of things with them. And then there's going to be another bit of memory they get put into, and then as and when the network interface is ready to put more voltages onto the wire, it can do that. But memory is a finite resource, so if it's full at the point that some set of voltages arrive on the wire, then that data's gone forever. Or maybe it's, technically speaking, recoverable from the effects it had on the surrounding area, and that's quantum-y stuff that I don't know anything about, so we're not going to go down that route. So the network's unreliable. We need reliable communication, and how we do that is through convention. So one of the questions I like to ask people here is, how do you know if someone got the letter you sent them, ignoring things like recorded delivery that some postal services offer? And the only answer really is, in your letter, or ahead of time, you ask them, when I send you a letter, send me one back acknowledging that you received my message. And if I don't get an acknowledgement, after a while, I'm going to send another letter, I'm going to try again. And TCP is a convention that does effectively this. So it provides reliability for IP packets. So until now, we're talking about IP and these packets going from one machine to another. But there's no kind of reliability. TCP is a convention that adds that reliability, and we'll talk about exactly what that looks like shortly. But it also adds another thing as well. It adds ports. So we can have more than one conversation going on between two IPs. They're just a number. And like IPs, you need a source port and a destination port. And what that really looks like is, if I have a web server, for example, running, you might know that a web server listens on port 80. But what does that really mean? And what it really means is, when you start the web server, it tells the operating system, hey, by the way, if you get any packets that arrive that are tagged with 80 as the destination port, give them to me, please. And when you make an outgoing connection, you have a source port. So I think you probably ask the operating system, hey, give me a source port for this communication. And then when the data comes back, it's kind of as though you're listening on that port. The terminology doesn't quite work out that way, but yeah. And if you don't need the reliability TCP provides, you can use UDP, which just adds ports and doesn't do the reliability thing. So it's kind of like, almost like raw IP, but you get ports too, so you can have multiple things listening and talking, which I think is a very worthwhile thing, because I don't know about you, but I tend to have more than one application running on my computer at once. Let's check the chat. When we talk about ping, does this also have anything to do with the data transfer and packet loss, or is ping completely different? Ping is a protocol that runs over IP called ICMP, and I can't remember what it stands for. It's like the Internet Control Messaging Protocol. We're going to have to look it up, aren't we? ICMP. It's the Internet Control Message Protocol. I think that's what I said. Yeah. Which is basically, the short version at least is, you send out an ICMP packet, and machines, generally speaking, are configured to reply to you with their own ICMP packet, and you can track the timing between when you sent one and when you got one back, and that timing gives you a thing called the round trip time, or the network latency, how long it took to get one message there, one message back. Yeah, cool. I think that's all the questions. Cool. So let's talk TCP. So if I want to have a TCP connection between two machines, this is kind of what it looks like. So we've got machine A and machine B again. And machine B says, hey, can we talk? Machine B says, sure. Machine A says, okay, let's talk. That's what we call the three-way handshake. And don't worry, we'll use the actual terminology on the next slide, but for now. And then we kind of have the data bit of this conversation. So the convention is when one side sends some information or some data, the other side acknowledges it. So machine A might say, so can you do this thing for me? Machine B says, yeah, I hear you. Sometime later says, here's the thing you wanted. Machine A says, got it. And then one of them machines decides that it's time to end the conversation, as it were, and says, I'm leaving. It's a very passive-aggressive machine. Machine A says, fine, me too. Machine B says, good. And at that point, the TCP session, as it were, is considered to be terminated. So that's kind of the analogy version. The real version is a bit more like this. So machine A is actually an IP and port pair. So we've got this is our source IP and the source port, and then our destination IP and destination port, which is 80 in this case, which is the default for plain old HTTP. So the initial packet is called a SYN packet, a synchronize packet, saying, I want to synchronize with you. Let us be synchronized so that we can talk. The second machine sends a SYN ACK packet, an acknowledgement of the synchronization request. And then finally, machine A sends an ACK, an acknowledgement packet back. That's the TCP three-way handshake. And then we get to the conversation part. So we get data one way and an acknowledgement back, and then data the other way and an acknowledgement back the other way. And then sooner or later, and there's more than one way to close down a TCP session, but this is one way. In this case, machine B wants to close the connection, sends a fin packet, a finish packet. Machine A acknowledges it, machine B acknowledges the acknowledgement. And there we go. And like that's all, fine, nothing went wrong in the situation. But in the situation where something didn't happen, so in this case, the sender didn't receive an acknowledgement after a while, it will resend the data. So we're kind of compressing the handshake here, we're ignoring it. So some data gets sent, an acknowledgement is received, and then some data gets sent in the other direction, some time passes. How long that is configurable in TCP settings and drivers and things. Did not receive an acknowledgement, and it will try again. And this time it does receive an acknowledgement, and then when the conversation's done, one side will terminate the connection. Or maybe this will fail over and over and over again, and after a predetermined number of failures, the TCP session will be considered dead. If, for example, someone with a JCP pulls up the network cable, that connection's pretty dead now. Someone's asked, would you mind sharing the slide link? Yeah, I can do that later. I'll share it as a PDF or something and tweet it. So if we were talking about the OSI model, at least, we're going to skip up to the top and talk about HTTP, an application layer protocol. And version 1.1 is just plain text. We're not going to talk about HTTP2 today. It's binary and more complicated, and we're going to ignore it for now. It might be encrypted with, say, TLS, but we're also going to ignore that. But when we're talking about application layer protocols, we can mostly ignore the lower layers, which is the nice thing about that layered model in general. And I put a note here to say, HTTP 1.1, it's so simple you can write it by hand. And I'm not, generally speaking, one to make claims without backing those up. So I'm going to give you an example of what HTTP looks like. So we're going to use this program Telnet to connect to example.com. And all Telnet does is it handles those lower layers, right, up to the TCP part. It establishes a TCP connection for us, but it doesn't know anything about application layer stuff, or HTTP or anything. It's just handling the TCP stuff. And our destination port is going to be 80. We get to specify that. And HTTP looks a bit like this. So we have a verb, something like a method, something like get or post, a path like index.html, and then the HTTP version. That's the first line. And then we get a carriage return and new line character. And we specify the host we're trying to connect to. In this case, it's example.com. The reason we do that is because the receiving end doesn't know what we typed here. DNS figured that out for us. We're connecting to an IP, and the receiving end needs to know. And this is basically the minimal HTTP request. So if we hit return a couple of times, so an empty line signifies the end of the request, and we'll get the response back. And the response looks something like this. So we get a status line telling us they're also speaking HTTP version 1.1. The status was 200 OK, and a bunch of these headers, which kind of give us metadata about the information. And in this case, also a content length, which tells us how many bytes we need to read after this. So we get an empty line followed by all of the HTML that comes back. And my TCP connection's still open, still sat there. I can send another request to get slash with HTTP 1.1. My host is still example.com. But in this case, I can tell example.com, when you've finished sending your request, I want you to close the TCP connection. So this is kind of an example of where the application layer stuff kind of dips down a layer into TCP stuff. So if I send that request, you'll see I get this message, connection closed by foreign host. So HTTP 1.1, pretty simple. So here is a kind of our example in the same context that we had our TCP conversation before. We've got a source IP import, that's on our client machine. We've got a destination IP import, that's our web server. We do a TCP handshake, and then the data that's sent over looks like this. And the acknowledgements and things kind of happen behind the scenes, so to speak. So the request part of the HTTP, like we said, each line in the request is separated by a carriage return and a line feed character. So a CRLF sequence. You might hear about CRLF injection, for example, is where you can inject, in some cases, your own headers into a HTTP response, for example. The request is terminated by two of them, and the headers are sent in the form key and value. And there's lots and lots and lots of different headers, including non-standard ones that start with X dash and that kind of thing. But just some examples of what these really mean. So we've got the request line with the method, get me the file at /index.html. By the way, I'm using HTTP version 1.1, the name of the host we're connecting to for the host. Connection we just seen in action, so it tells the receiving end, please close the TCP connection when you've sent me the data. And then we get kind of headers that technically don't really do anything, but they provide information to the server side. So the user agent, that would be like, what browser you're running, what version it is. That can be useful for servers, not just to do analytics and things, but some websites will also send you, for example, a different version of the website if you're using a mobile browser or something like that. I'm not entirely sure I agree with that practice, but there you go. Other headers, things like accept. So telling you what kind of data you'll accept. This might be accept text/HTML or application/JSON or something like that. Or here, ***. I'll accept anything. And then the response, again, also separated by CRLF sequences, and the response body separated from headers by two of them. So you get the status line. I think that's what the RFC calls it, although don't quote me on that. Saying, I'm also using this HTTP version, which tells the HTTP client how it should interpret the rest of the response. If this was 1.0, it would be slightly different. Or the response code, so 200 for OK. You've probably seen other response codes, things like 404 is probably the most likely one you'll have seen. The general rule is if it starts with a 2, it means things are all right. If it's a 3, it means you should go somewhere else. A 4 means the client screwed up, and a 5 means the server screwed up. It doesn't always quite work like that, but that's the way I think of it. Also get a description of the content type, so how probably this is going to be a web browser should treat the data that's coming back, whether it's JavaScript or HTML or whatever. The content length. Also, say after you finish with the headers, you need to read 1,337 bytes to get all of the response body. That's very useful because, how else would you know unless you've told it to close the connection? And then a great deal of other headers, things like location headers and things, which can have an effect depending on what the response code is and what the client wants to do and so on. But the point is, HTTP, when it comes down to it, it's a really pretty simple protocol, which I personally happen to think is nice. That's a good thing. So we've been talking about IP addresses a whole lot, but it'd be good to know at least a little bit about DNS, because I don't know about you, but I would much rather remember example.com instead of 93.184, etc. And if you want to talk about IPv6, I really can't remember this at all. So we use this thing called the domain name system to translate names into IP addresses in a variety of ways. So DNS uses UDP most of the time. It uses TCP in a few situations, but we're not going to get into those. And it usually listens on port 53 UDP. So UDP ports are different to TCP ports. So this is, if you recall, some software running on a server somewhere, and when it started up, it told the operating system, hey, when you receive UDP packets that are tagged with port 53, give those to me, they're mine. So clients request records from DNS servers, and it kind of looks like, and those records, there are different types of. So this is a non-exhaustive list. Each record is stored against some kind of name. So a name might be something like example.com, or it might be subdomain.example.com. That's the name part. And the different types that we'll cover here is we have an A record or an address record, which is an IPv4 address. So for example.com, it would be this one. There's also 4 A's, or the A record, which is an IPv6 address. We also get C names, canonical names. So they are an alias for another name. So that's very useful when you want to refer to something, but you have no guarantees about what its IP might be. So its IP might change. Very useful when you're using things like CDNs and so on. MX records are a mail exchange handler. So if I want to send mail to someone at example.com, my email client would look up the MX record for that domain. We get the NS records as well, the authoritative name server for a domain. So which DNS server effectively we should go to find out, get records for a particular domain. And we get text records as well, so some human readable text, and they get used and abused for all kinds of things, from verifying that you own a domain to setting some things to do with email which were kind of backcode onto it. Yeah. But again, not an exhaustive list, but just to give you an idea of, there's this directory system where we're looking at records that look like this. So an example lookup then is, DNS queries use UDP, as we've talked about, so there's no handshake. Well, that kind of means it could be difficult to correlate requests and responses, right? So when we're talking TCP, we had this whole conversation, a TCP session with source ports and destination ports and things, and there's other things that we didn't talk about, but we knew what conversation every segment was a part of, because TCP does that for us. UDP doesn't really. So if I'm going to send out a request to a DNS server saying, what IP address is at this name, and I get a response back that's just an IP, how do I know what it's an answer to? And the answer to that is the response includes the question. So when we send a query, it'll be something like, I want the A record for example.com. The answer will come back, it includes the query, so that you can do that correlation. And again, this isn't actually plain text, it's a binary thing, but it turns out binary is quite hard to read in slides. I have a question, where can you find the slides for this? I'll tweet a link to them when I'm done streaming, because I haven't done that yet. So that's DNS. CNAMEs, worth dwelling on a little bit. They crop up quite a bit in things like subdomain takeovers. So, we need an IP address to make a connection to a host. We can't connect to a name. You can't send an IP packet to the name instead of an IP. But there's no A record for the name. But if there is a CNAME, the DNS server will respond with the CNAME record and the A record for that name if one exists. So here our query is, I want an A record for example.com. It turns out there isn't one. There is in reality, but in this example. So the response come back saying, well, the query was for an A record for example.com, but actually there's a CNAME for example.com instead. And that points to origin.example.com, and that itself is a CNAME for webserver.example.com, and that has an A record, which is 93.184.216.34 in this example. So, you don't have to ahead of time figure out, I might have to, is there an A record or is there only a CNAME and I need to work that out as a client? You don't. The server works that out for you. If you ask for an A record, it will try its damn hardest to get you one, which is awesome. So something you might see at the other end of a network is a load balancer. So, one server is rarely enough to handle all of your traffic, or at least for the target audience for that this slide deck was originally for. That was definitely true. I was working at a company who, their background load never really fell below about 500-600 requests a second, and at many times was in the tens of thousands. So you need more than one web server. So you might use a thing called a load balancer to do that. And as I think many of my audience are people doing bug bounty and that kind of thing, I think it's important to know a little bit about load balancers and why they exist and what they do. So some of them work at the transport layer. So TCP load balancers, they're the relatively simple ones, and they split traffic between multiple servers. Others, though, which are a bit more interesting, work at the application layer. So transport layer ones are kind of easier. They require less CPU time. But application layer is more powerful. So you can send requests to a particular HTTP endpoint to a different pool of servers. So requests going to example.com /login can go to a pool of servers that handle authentication, and ones that go to /anything else go to a different pool of general application servers, and so on. And for some requests, you can respond to them without even hitting a backend server at all. So things like redirecting you to a localized version of a website, or from a URL that doesn't exist anymore to a new one. You can do that fully in a load balancer without having to hit your application servers at all. Both kinds of of load balancers, use different load balancing algorithms. So they can use round robin, or weighted round robin. So where they just go, first request goes to one server, next one goes to another server, next one goes to another one, and so on, round in a circle. Or you can use least connections load balancing, where the load balancer keeps track of how many connections are currently active to every given server, and any new connection arriving will go to the server with the least number of connections. You can have them hashed on some property of the connection, like the source IP as well. So, or in an application layer load balancer, might be some HTTP header like the user agent, so that any connection coming from that IP in this case, or that user agent in the other case, will always hit the same backend server. Or it could be random as well. And there are others as well, but they're kind of the main ones that crop up. So transport layer load balancers, they deal with TCP level stuff. So all packets for a particular TCP session get sent to the same backend server. And the advantage of that is it works for like basically any TCP service. So it could be a database server, it could be a web server, internet-enabled toasters, anything like that speaks TCP. They can work for UDP too, but the application layer protocol on top kind of must be stateless, or you need to use hash-based load balancing. Things can get a little bit tricky that way. But big advantage, no need to decrypt the traffic in transit. So if the traffic's TLS encrypted, a transport layer load balancer still can work with that fine, because the destination IPs and source IPs and ports and things, they're all still in plain text. It's only the data that's encrypted. So they can still work for that. And requests can only be split based on transport layer stuff. So you end up doing things like least connections load balancing, fairly limited in their capabilities generally. Much more interesting though, the application layer load balancers, they actually understand the application layer protocol. And probably the most common kind you would come across is HTTP, but they can technically exist for anything. So, I think it was YouTube developed a MySQL load balancer effectively. They might not call it a load balancer, but it kind of is. And I think it was called Vitesse, that did all kinds of in-flight query rewriting and stuff like that. Very cool, but it doesn't have to be HTTP. But you have to write every application layer load balancer specifically for its application, or someone has to. But unless you do really useful stuff like split request based on application layer details, like the HTTP path, the query string, the cookies, and that kind of turns out to be quite important when you're trying to do recon on a site. You might think, this target has only got one domain. But there might be many different web servers with different configurations behind that one domain, and there's a load balancer in the way that's changing what you hit depending on what your path is, your query string, or even your cookies as well. I know for a fact there are systems out there which, if you have a particular value in your cookie, you'll be hitting a different pool of servers running completely different tech, whether that's through migrations or from one tech to another that are currently in progress, or for other reasons. It definitely happens. Again, as we mentioned, you can respond to some requests without hitting a backend server at all. So like redirecting HTTP to HTTPS. So it might be that you've been trying to break some redirect and turn it into an open redirect on one part of an application, and then you see something on a different part of the application, and you think, oh, well, the same rules will apply, but not necessarily, because it might be being done by a load balancer. They can also do edge-side includes. That's something I think to look out for. I know that Cloudflare support edge-side includes. Some other load balancers do as well. You can also, block requests that you suspect are malicious. So like an HTTP request containing a possible cross-site scripting payload. Hard to do properly, but it definitely does happen. The downside, though, is it takes a lot more processing power to run an application layer load balancer. They are only made for one protocol, so like you can't use an HTTP balancer to balance MySQL connections. Just doesn't work. And if you're using encrypted transport like TLS, like basically everyone has these days, it means you have to decrypt the incoming traffic before it can be processed. And that means, that's probably okay. But it means your private keys have to be accessible by a load balancer so it can do it. It takes a certain amount of CPU time. And also, in some situations, you might have to re-encrypt as well. So, like if you've got card holder data running across an internal network, you probably want it to be encrypted anyway. So application load balancers. And I think this is around one of the last things that we have to talk about here, actually. So network address translation. It's something that almost certainly happens on your home network. So, IPv4 space is kind of limited. There's only like 4.2 billion IP addresses around, in theory, at an absolute maximum, because they're just a 32-bit unsigned integer, and that's max int. But there's a ton of reserve ranges as well, so actually it's only 3.7 billion-ish. this was when I wrote this slide deck, March 2018. There were 7.6 billion people on Earth. That's more than their IP addresses. I like, how many internet connected devices do you have? Because I know I have a lot. And that is a solution to the IPv4 space problem, but also a good way to make sure your network is really actually private, because private addresses can't be routed from the public internet. So you get these reserved ranges. So you've got 3 main private ones, 10 dot something, 172.16 dot something, and 192.168 dot something. And if you remember this Cedar notation, we get a /8, a /12, and a /16. We've got the local and loopback ranges, 127 dot something and 0 dot something. And there's like 10 more ranges that are reserved for a bunch of different reasons, like documentation and broadcast ranges. And the most annoying one, future use, which is, someone wrote that in the late 80s, early 90s or something like that, maybe even earlier. Like, this is for future use. And then they never did. It's 2021. I'm pretty sure it's the future now. We should probably be able to use them. I have a question. Did you learn networking from a book or course like CCNA or Network Plus? Not a course, that's for sure. I did read about networking in a book a very long time ago. I'd guess around 2002-ish or something like that, from a big orange book called Networking Complete. I think it was Cybex Publishers or something like that. Networking Complete book, 2nd edition. Yeah, Cybex. So I read probably the 1st edition of this at an age that people thought it was weird that I was reading a book about networking while I was on holiday. It was a long time ago. It really was complete. Yeah, so it was just published 2001. So there's a bunch of stuff it won't cover, for example. But I read that to kind of get an idea initially, and then most stuff that I learn, I just tend to Google as and when I need it, or I do experiments to figure stuff out. So we only have 1 slide left, so I'll show you some of that when we're done. So the great thing about network address translation is I originally thought, it must be scary and complicated and that sort of thing, but we kind of already know how it works, or we know enough to figure out how to implement it in a way. So we have, machine A on my home network behind some network address translation. It wants to connect to Google's DNS servers, 8.8.8.8. Nice, easy to remember IP. Machine A sends a packet. The source MAC is all A's, the destination MAC is all C's, if you remember that from earlier on. That's the internal interface on my default gateway. The source IP is my internal private IP, 192.168.0.10, and some source port that I was allocated by my OS. And the destination IP port is 8.8.8.8, destination port 53. Now the default gateway receives this packet, and like the router that we talked about at the beginning that rewrote the source and destination MAC addresses, that happens, but it also rewrites the source and destination IP. So the source IP becomes the public IP of the router and some other source port, and the destination IP and port stays the same. And that translation is recorded so that the return traffic that comes back from the DNS server can have its destination IP and port translated back to my internal IP and port. I was really quite pleased with that, because I originally didn't know how NAT worked and was like, it must be really complicated. But after I sort of sat down and figured out how routers work in the first place, it turned out to be actually, kind of simple. So I said I would kind of show one of the ways I sort of figure things out and Google for things. And for networking, I think one of the absolute best things you can do is run Wireshark. So if you're not familiar, Wireshark is a network analyzer, and I'm going to guess that my font size isn't super great on here, so I'm gonna bump it up a little bit. And what I'm going to do is go to capture and options, and I'm going to select my main my network interface, and then I'm going to get ready to run a curl command here to example.com. So I'm going to hit start. I'm going to run that connection. I'm going to go back to Wireshark, and I'm going to hit stop. And we're going to take a look at a real HTTP request in Wireshark, just to prove that I wasn't talking a load of bollocks. So I typed HTTP into this filter window here, and you can see it's got two things here with protocol HTTP. I'm going to do is right click on one of them and then go to follow TCP stream. So this by default pops up a window showing me all of the text that was transmitted. So this should hopefully look quite familiar. This is our request. Here's our response. But the really interesting stuff is back here. So this is all of the TCP segments and things that were associated with our HTTP request. So we get the very beginning, we get a SYN packet. So this is going from source 192.168.38, which is my local machine, and the destination 93184.216.34, which is example.com. And we can see the source and destination ports here, 35130, which was chosen by my OS, and 80, which is the default for HTTP. So we can see that SYN packet on the first, then we see the SYN ACK in the other direction. So note the source and destination IPs have swapped, and so have the ports. And then we get the ACK. Then we get the HTTP part, the ACK for the request, and then we get the response, the ACK for the response, the FIN with an ACK flag set, the FIN ACK, and then the ACK at the end. That's the termination. So it looks like we got that fairly accurate in the slides, which is awesome. But we can drill down into things down here as well. So we can see, helpfully, this has been split into a few layers for us by Wireshark. So we have our frame, which is just kind of like the raw information. Decoded Ethernet information. So this is our Ethernet frame. It has a destination and a source MAC address. And here, this is going from my machine to example.com. So the destination MAC will be the MAC of my default gateway, and the source is my local MAC address. And then just something that tells us what type of data is included. In this case, it's IPv4. And then we can look at the IPv4 information. So we get the source IP is my local private, the destination one is example.com's IP. There's a bunch of flags telling you about what protocol is being used and the length and stuff like that. But and then we get the TCP layer information, which in this case mostly is the ports is the useful, interesting bit. That's the bit we've been talking about. So the source port is some high numbered one that my OS came up with. The destination is 80 for HTTP. And if we were looking at an HTTP packet, we'll get an extra layer as well. So all four layers of the Internet Protocol suite. We get the link layer where we get Ethernet frames and things. The IP layer where we get IP addressing. The transport layer where we get ports and transport control, and then we get HTTP on the top of that. So highly recommend you have a play with Wireshark and just have a play around and see what networks going back and forth. Start capturing things and then turn your network interface off and back on again, and see if you can figure out how DHCP works to allocate an IP address, because the stuff that we talked about early on doesn't quite explain how that ends up working. But Wireshark definitely is good fun to have a play around with and learn a bit more about it. And if you don't understand something, you can Google for it and find out what it is. That's the way I tend to learn, at least. Let's have a look at the chat. So Sev73 says, "Hi Tom, can you do a feature session on Linux, please?" Quite possibly. I think I do have a slide deck for the Linux stuff, but I'm not super happy with that. I'll probably try and come up with something else. Redhawk5 says, "Hi Tom, can you do a similar video to the one you did with Stock, talking about using JavaScript for hackers?" Yeah, I'm planning to do some more stuff with Stock. We don't know what yet. And will I upload the stream? Yeah, I will. I'll upload the stream, don't worry. So I am quite hoarse at this point. I've been talking for a while. It's been an hour and 22 minutes. It was a real quick blast through networking as a concept, and there's a whole bunch of stuff we didn't talk about, but I wanted to try and give people at least a mental model for how computers talk to each other so that they can find out more for themselves. And I think for a lot of people that's the really hard part, is how to get started. And hopefully this has helped at least one person get started. So thank you all for listening to me drone on, and I'm going to go and get a drink. So have yourselves a lovely evening, morning, afternoon, or whatever time of day it is where you are, and hopefully I'll see you soon.